Hello everyone. Today we're going to do the last section in the section 3, chapter 2. It's about the symmetricities of functions. Here basically we're going to talk about two different types of symmetricities. First one is called the y-axis symmetry and the second one is called the origin symmetry. To be more precise, we say even functions are y-axis symmetry and odd functions are origin symmetry. So what do we mean by even functions? If a function satisfies this equality for all the values of x in the domain, so then we call that function is an even function. So that means, let's say we have a function f and we are plugging negative x to that function, and that is same as plugging positive x to the same function. So if this satisfies for all the x values in its domain, then this f function is called an even function. So on the other hand, if the f of minus x equals minus of f of x for all the values of the domain, all the values in the domain of the f function, then we call that function is an odd function, and that is origin symmetry. Even functions are y-axis symmetry. So let's look at an example of an even function. So this is fx equals absolute value of x plus 3. This function is an even function. Let's see how that can be proved. Here I'm plugging negative x to this f function negative x, and that means we want to take the absolute value of negative of x. So we know that this becomes positive x because of we have absolute value here, and then absolute value of x plus 3. So this term is exactly the fx function that we are using. So that means we started with plugging negative x and have ended up with getting f of x again. So it doesn't matter what the x value is we are plugging, f of negative x is always f of x. So that means f is an even function. So this is the graph of that function f. We know that this is a vertical transformation to the parent function f of x equals absolute value of x. So there is a 3 units upward vertical transformation. So that means it starts at 3 here, and the shape of graph is like that. Here again you can see that this y-axis kind of acting as a mirror, and this is the graph is the mirror image on the other side. So this is an even function and it is y-axis symmetry. The next type is f of x equals this function, and here I'm plugging negative x again, but here this becomes 5 times negative x to the power 3. This is an odd power minus, and this minus is coming from the function, and here we are plugging negative x here, so that becomes positive x, and here 5 times negative x to the power 3 becomes negative 5 times x to the power 3. Since this is an odd power, here we are getting a negative sign, and this time this term becomes positive. It's negative times negative becomes positive here. So now if we factor out negative 1 or negative sign, then we can get 5x to the power 3, and this becomes negative x since we are factoring negative sign or negative 1 here. So that means what we have obtained negative times this term. This term is nothing but our fx function. So that means f of minus x equals negative of f of x. So it doesn't matter what is your x value that you are plugging here, f of minus x is always negative of f of x. So that means this function is an odd function, and this is the graph of that f function. This is the polynomial with the degree 3, and what we mean by the origin symmetric here is if you pick a point on the graph and draw the line across this point or that point and the origin, that line should always crosses another point which is the same size and the opposite sign. Now if you look at this polynomial, this is our second degree polynomial, and now if you plug in negative x here, negative x to the power 2 minus 3 times negative of x plus 6, but we know that this is negative x to the power 2 becomes positive x to the power 2, and here negative times negative becomes positive 3x and plus 6. But you can't make this function to be equals to f of x or negative of f of x. So this is never equals to the f of x again, of f of negative of f of x or f of negative x. So it has no any symmetricity, so we say that it is neither even or nor odd. So but whenever we deal with polynomials, there is an easy way to identify whether the given function is an even or odd function. Let's say we have a polynomial with only even exponents, so only even powers, and then we can say that that polynomial is an even function. And if we have polynomial only with odd powers, odd exponents, then that polynomial is an odd function. So this is an example of that. In this example, all the powers are odd powers. The 3 is an odd number, and here we have one odd number, so that is exponent, all the odd exponents. All the exponents are odd exponents, odd powers. So that means this is an odd function. And if the polynomial is containing both odd and even, like this, here this is an even power and we have an odd power, so it's containing both of these combination, then that polynomial is neither odd nor even. So that is the last topic in the section 3. Now let's move on to the section 4. Here, since we have already learned about functions, so now we're going to do some operations with functions. Basically, we're going to talk about 5 basic operations with functions. And let's say we have f and g, two functions. We can define a new function by adding them, which is called the plus operation, or the addition of f and g, so which is defined to be the f of x plus of and g of x. And similarly we can define the difference of, or f of f minus g function, so which is f of x minus g of x, and the product of those two functions, which is the product of those, and the division of f over g to be the f of x divided by g of x. But here we need to make sure that this gx is not 0, otherwise this function is not defined or does not exist. So let's look at an example of two functions, and we can do the operations on it. So here we have two functions, fx 3 times square root of x minus 2, and this second degree polynomial gx function. And here I'm taking f plus g. This is f plus g, and I want to find the value of f plus g, this new function, at the point 4. So that means f of 4 plus g of 4. So that means f of 4 is, we can find the value just by plugging 4 here, because this is the fx function. I'm plugging 4, so that becomes 3 times square root of 4 minus 2, plus plug in 4 here to the gx function, so that is 4 to the power 2 plus 5. So now if you simplify it, we can get 4 by the f function. Why? Because here we have 3 times the square root of 4, that means 3 times 2, because square root of 4 is 2, so 3 times 2 becomes 6. 6 minus 2 is 4, and here 4 to the power 2 is 16. 16 plus 5 is 21, so that means we get 4 plus 21 becomes 25. And we can do the same thing just by taking the difference of those two functions, and here I'm finding the whole function just by plugging x. No, there's, I'm not plugging a special number here, just for any x value. So that means the difference of f of x and the gx, and that means we need to take the difference of this function and this gx function. Now we can do the FOIL here and we can get negative x squared minus 5, and we can simplify this one now because we have 3x minus x squared that can be simplified, but here we have two numbers that can be simplified to negative 7. So this is a new function by taking the difference of f and g. And similarly we can do the product. Let's say we want to take the product of f and g at the point 0, so that means the product of f at 0 times and the product of g at 0. So that means we need to plug in 0 to the f function. That's 3 times square root of 0 minus 2, that becomes negative 2 here. And when you plug in 0 to the g function, that becomes 0 to the power 2 plus 5. So now we take the product, that becomes negative 10. And we can do the same thing for the division, g over f over g of 9, that means f of 9 divided by g of 9, and you get the idea. Now the other question is that since now here we are making new functions called g f plus g, f minus g, f times g, and f divided g, and we should be able to determine the domains of those new functions. So how do we find them? First we need to find the domain of f and the domain of g, and then the domain of f plus g, f minus g, or f times g is just the intersection of those two domains of f and g. And the domain of f divide g is the intersection, but intersection excluding any points where the gx becomes 0. That because gx is in the denominator. So let's see how we can do that. Here I'm taking two relations, and this first represents the function f, and the second relation represents the function t. You know how to read a relation in terms of function here, because it means if we plug in 1 to this f function we can get 2, and if we plug in 2 to the f function we can get 8, and so on. And now let's determine the domain of f. We know how to find the domain of a function whenever we have this relation form. That means all the first coordinates of these pairs. So I'm collecting all the first coordinates, that becomes my domain of the f function. That is 1, 2, 3, and 5. These are the 4 numbers in the domain. And the domain of g is the same way, taking the first values, the first x coordinate, the x coordinate of the ordered pairs. That is 1, 2, 3, and 4. So now let's say we want to determine the domain of f plus g, minus g, and the product, these 3 functions. So that should be the intersection, or in other words the common values of the domain of f and the g. So here these are the common values in these boxes. You can see the 1, 2, 3, and all these 3 numbers are common. So then the domain of these 3 functions containing these 3 values, 1, 2, and 3. So that is the domain of these new 3 functions. But this becomes different now, which is whenever we do find the division of f and g. So here we have to exclude any point where g becomes 0. So here we know this is the intersection of f and g domains. So now we need to check each point in this intersection, and if it gives any, if it makes g to be a 0 value. So here I'm plugging 1 to this g function first, and then I can get 6. So that is non-zero. And if I plug in 2 to g function I get 11. But when I plug in 3 to g function, you can see that we get 0 as the output. So then that means we need to exclude the point 3 from the domain of this domain of for the domain for the f over g function. That means only the 1 and 2 is remaining here. So this is the domain of the f over g function. So, and then now you can find the relations regarding corresponding to this f plus g function. It's like, you know, the domain of f plus g is 1, 2, and 3. So now if we plug in 1 to this new function, that means f of 1 plus g of 1, but we know what is f of 1 and g of 1. F of 1 is 2, so here we have 2 plus f of g of 1 is 6, so that here we have 6. That means 2 plus 6, that becomes 8 here. So that is by plugging 1. So we can do the same thing for the second value in the domain 2. I'm plugging 2 to f function, I can get 8. Here I'm taking 8 here, plus, and I'm plugging 2 to g function, that gives me 11. So then we have 11 here. So 8 plus 11 becomes 19. And the last value in the domain of f plus g, plug in 3. F of 3 is 6. Here we get 6 here, and g of 3 is 0. So it's 6 plus 0, that becomes 6. So this is the relation of the f plus g function. Likewise, you can find all the other combinations, operations of f and g now. So that's how we deal with relations. Now let's see how we can find the domains of f plus g and the other combinations of f and g whenever we have the domains of f and g as intervals. So here we have the domain of f. This is the function f square root of x. We know how to find the domain of x. You know that as we talked before, that this function, we can't plug in any negative values to this function. The domain is always positive numbers, including 0, because we can find the square root of 0 is 0. So it's starting 0 and all the other positive numbers. And the domain of this gx function is, this is just a line, so we can evaluate at any point. That is just the whole real line, negative infinity to positive infinity. So all these two domains are in interval notation. And now let's say we want to determine the domain of f plus g. The same concept here, we need to find the intersection or common values for this of these two intervals. The first one is starting at 0 and goes to infinity, and the second one is taking all the values in the real line. So the intersection, it is clear that intersection is only there, the common values is only from 0 to infinity. So that is starting at 0 and go up to infinity. So that is the domain of f plus g function. And the domain of g over f is, so we need to exclude if there's any point that if this f function becomes 0 from this intersection. So we know that at 0, if you plug in 0 to the f function, that becomes 0. So that is in the denominator. So we have to exclude the point 0, and this f function never becomes 0 after that for any positive value here. So then this is the only point, 0 is the only point that we need to exclude from this intersection, and then we can get the domain for this g over f function. You can easily see that we can verify this, but if you write down the equation of g over f function, so that is g x over f of x, that is this line 3x plus 1 divided by the square root of x. You can see that here that this x should not be, this denominator should not be 0. That means x should not be 0. So that means x 0 is the only value that we should exclude from this intersection. So likewise, we can find domains of any combinations of functions. So I'm gonna stop here for the class. For the today's class, we can start from the next topic in the Wednesday. And have a nice day.